So we're going to be moving back to mechanics. So when you're thinking about keeping your work and stuff organized, this is going to be going back into mechanics. But there's a reason that we were doing mechanics for a while with our Suvat equations. There's a reason we jumped back to do integration, because we're going to need to use integration in this topic that we've got here. Okay? So variable acceleration. I've said this is year 1 because we come back to it again when we go into year 13 as well. But we're just going to talk about functions of time. So up until now, the acceleration has always been constant in any particular period of time. So even in this curve that we've got here, I should call it a curve, not really that curvy, there's constant acceleration here, constant acceleration here, constant deceleration that we have here. So there's always constant acceleration for each separate bit that we've got. Now this is not realistic, because there should be a smooth change from acceleration to constant velocities. Okay, we don't actually in real life have something that is constantly accelerating and then suddenly it's not accelerating at all. So if they ever ask you something about what is unrealistic about one of these graphs that we have here, something that is unrealistic is that there should be a smooth change from acceleration to constant velocity. That's the kind of little 1 or 2 mark question that they might ask you about here. Obviously, these are our velocity time graphs that we have. So it is actually possible to specify either the displacement, the velocity, or the acceleration as any function of time, i.e. an expression in terms of t. So instead of the curve being, I don't know, y equals x squared, you can have something like the velocity equals a half t cubed, where if you want to find out the velocity, you take the time that it's been traveling for, you cube it, and then you half it. What this allows us to do is it means that we can have the acceleration can be constantly changing. It can be a variable acceleration. What did we say in a velocity time graph was the geometric property that represented acceleration in a velocity time graph? The gradient. Yeah, look, in this velocity time graph, this was positive acceleration. When it had a flat part, there was no acceleration, the gradient is 0, and here we had a negative gradient, so it was a deceleration. So how would we describe the acceleration of this particle that we've got here on that velocity time graph? What could we say is about its acceleration as time goes on? It's increasing. The acceleration is increasing. How can you see that it's increasing to me? Yeah, it's getting more steep. As you go across, as the time goes across, it's getting steeper and steeper. So the acceleration is also accelerating, if that makes sense, which kind of does, but we don't think of it in those kind of terms, right? But before we do that, before we actually start doing any of the curves or the differentiation and integration that we know we're coming across, I just want to make sure that we're comfortable with using formulae that are in terms of v and t rather than in terms of y and x. So the velocity time graph of a body is shown above, which was this graph that we have here. And all it wants us to do, where it says v is equal to a half t cubed, all it wants us to do, it says what is the velocity after 4 seconds have elapsed. So really, it's telling us that the time is going to be equal to 4. So if I want to find out what the velocity is for part A of the question, velocity is just going to be a half times t cubed, which is a half times 4 cubed. So the velocity is 32 meters per second, okay? I'm just wanting us to start getting used to using some of these different kinds of notations and letters and things. And then for part B of the question, it says how many seconds have elapsed when the velocity of the body is 108 meters per second. So this time, they're telling us, that one they were telling us that t was 4. This time they're telling us that v is 108. So all we do is we go to our equation, which is that v equals a half t cubed, and we find out what value of t will give me a value of v is 108. So I'm going to double both sides, so I get 216 is t cubed. Anyone think they know what value of t is the cube root of 216? I've got an idea. Six. So t is equal to 6. I only know a few cube numbers. I should know all of them. But like I know 7, so I thought, oh, 7 is 243. No, 343. So I knew it had to be somewhere smaller than that. I was just guessing, really. Could have thought about it. So super simple, right? All we're doing is we're extracting the information from the question, 4 seconds. In this one, v equals 108. Now, before we move on, can you have a negative value for v? Yeah, you could have a negative value for v. What would that tell you if you had a negative velocity? Good. It's telling you about the direction. It would be telling you about it might be going in the opposite direction to before. So you can have graphs that might look like this for a velocity time graph. Okay? Can you have negative values for the acceleration? Yeah, you can have deceleration, can't you? Can you have negative values for the displacement? Yes, because if you had a negative displacement, if I'm facing this way towards the window, negative displacement is behind me towards the door. Okay, so just to start thinking about how all of these things come together. So we're going to have a look at a different example that we've got here. It says a body moves in a straight line such that its velocity, v meters per second, at time t seconds, is given by v equals 2t squared minus 16t plus 24. Now, before I even go on with this question, you will know that this is not a SUVAT topic because you can see that the velocity is being given as a function of time. So you can't do SUVAT because the velocity is a function of time. And that's why we're already going to start thinking nothing to do with SUVAT here. Variable acceleration, nothing to do with it. They will... I can maybe think of a scenario where maybe they might get you to come up with what the equation is, but I would say 95% of the time, they will either tell you what the velocity equation is, the acceleration equation, or the displacement. But at the moment, we're just going to focus on velocity. So, first thing it wants us to say is the initial velocity. We're going to go through the whole question before even doing the maths. What does it mean, initial velocity? What value do I know about? T. I know that t is equal to 0. Okay, so that's dead easy. Part A of the question is just t equals 0. The values of t when the body is instantaneously at rest. If the body is at rest, what do we know? V is 0. Okay, now this word instantaneously means that it might not come to rest and then sit there for a while. It might mean a bit like when we threw a ball in the air and when the ball gets to the top and then comes back down again. At the top, we would say it's instantaneously at rest. It's at rest just for a moment. You remember that video of me throwing the rock up in the air? Even though it wasn't staying rested at the top, it rested there for an instant. That's why we say instantaneously at rest, okay? It then says, find the value of t when the velocity is 64. Well, very obviously, the velocity is equal to 64. And then it says the greatest speed of the body in this interval that we've got here. And we're going to think about many different ways that we might like to think about this one when we get to part D, okay? So we're going to go through nice and quick through these beginning bits. First of all, the initial velocity when t is equal to 0. Well, v is going to be equal to 2 times 0 squared minus 16 times 0 plus 24. But you know what? It's a one-mark question. You could probably spot straight away that v is equal to 24 because all of those t values are going to disappear when you have a 0 with them. So although I'm doing this now because I'm on the board, if this was a one-mark exam question, you could probably just say v is 24, couldn't you? You can just see that from there. Part B of the question, it says that v is equal to 0. So I'm going to get this here, and I'm just going to say 0 equals 2t squared minus 16t plus 24. It's a quadratic. We can factorize this. I'm going to factorize this, but if you want to do it on your have you done it on the calculator already, Shahan? How much? 6 and t equals 2. I mean, that's an easy one we could have factorized, but if you're quick on your calculator, why not? So we found the 2 times when the body is at rest. And we now want to find the value of t when the velocity is 64. So this time, because v is 64, I can replace it. So 64 is 2t squared minus 16t plus 24. What do I need to do? Make it equal 0. And then you can either use a calculator or we can factorize. I'm going to factorize if I can. Yep. What does it factorize to, anyone? Okay. Do both of those values for t make sense? I don't think the minus 2 makes that much sense. Because although it does have, we could interpret it as if it was continuing on that journey in the past, that's when it would have been 2 seconds ago. But generally, we want to take t as being greater than 0. So I think it probably makes sense to just say that t is equal to 10 that we've got here, right? Now, part D of the question is the one we didn't decide what our strategy was going to be. But we want to find the greatest speed of the body in the interval t between 0 and 5. So are there any suggestions of what kinds of things you might try and do to find the greatest speed of something? I'm happy to go. There's many different ways we could do this. What about if instead of saying greatest speed, what about if I said maximum speed? So we could do a turning point, actually. Actually, I think I've probably misled you a bit. I've misled you by saying a turning point because it might not actually end up being the maximum speed. What we're going to need to do for this is I think what might be helpful for us visually is to see what the graph looks like. I think that might be a good sort of starting point for us to think of what's happening here. So I'm going to draw a sketch of this quadratic, and actually I've got loads of the information already done for me. What information can I add onto my graph that's already on the board? The roots, okay, so the root, what are the roots, red one?
10 and -2.
That's for when the velocity was 64, so no, not for that bit. T equals 6 and t equals 2. So here's going to be my t equals 2. Here's going to be my t equals 6. So those are the roots. Why were they the roots and not this one? Because that's when it equals 0. Okay, good. Is there anything else I know about? We know it's crossing at 24 as well, because when t is 0, it's 24. And we know the shape. So we've got this bit like this. Okay? Not nicely drawn quadratic that I've got there, but you get the idea, okay? And we're interested to find out what the maximum speed is in that particular range of values that we've got. The range of values that we're interested in is between 0 and 5. So let's just quickly think on our graph. 0 is here, and 5 is going to be somewhere over here. So what does it look like the maximum speed is in that time? The maximum speed. The velocity. This is velocity along here. This bit of the graph is the velocity. This is the time. What is the highest or biggest velocity that it can have in between those two red lines that I've got here between 0 and 5? Careful. This is a velocity time graph. We're not trying to say about the gradient. The gradient would tell us when it had the highest acceleration. We just want to know when does it have the highest velocity. People have been saying it, but I just didn't hear. I couldn't hear who said it. That's what you were saying. When t is 0, the velocity looks like it's greatest. Okay. When t is 0, we have that it's at 24. But it's actually asking us about the greatest speed here. So we do need to be careful, because actually, if this goes down to minus 25, then it would be faster, because minus 25, the magnitude of that, is bigger than 24. Do you see what I'm saying in that difference there? It doesn't have to, when we're saying the greatest speed, we're not saying the most positive velocity, we're saying the greatest speed. So I guess the only thing I might want to check is, does that give us something that's any bigger? So I'm going to have a look and just check for myself. What value do you think I would put in here? We could find the minimum, but we also know about quadratics. Yeah, why would you put 4 in? Because 4 is in between 2 and 6. We know that this turning point here is going to be at 4 because of symmetry. So if I say that t is equal to 4, we get that v would be equal to 2 times 4 squared minus 16 times 4 plus 24. So that becomes 32 plus 24 minus 64. I've written that in the wrong order. 32 minus 64 plus 24. And what does that come to? Minus 8. Minus 8? Good. So minus 8 is actually only going down to 8. So I'm pretty convinced now that the maximum speed is going to be 24 meters per second. So the maximum speed is 24 meters per second. So the meaning of why part D is in that part of the exercise, or in that question, is to make us think, well, actually, sometimes we just need to draw a diagram. Sometimes drawing a diagram helps us visualize all of the different things that are happening here. And we don't want to make it too complicated by saying, oh, let's do the gradient of this, let's do the gradient of that. We just want to find out what the max velocity is that we've got there, okay? In that particular time period that it's got. Now, I've written in the corner we're going to do exercise 11A. I actually think 11A is pretty straightforward. I might get you to just do a few questions on it at home. I'd much rather us get onto some of the things that are a bit more kind of tricky. The only thing that we have in these is just subbing different values in and solving equations. So I want to push on to the next page, okay? So we're now going to think about using differentiation, and you can pretty much know where we're going afterwards. We'll be using integration. So earlier on, we saw that the velocity v is the rate of change of displacement. And that kind of even makes sense when we say meters per second. It is how is the distance changing with time. So it's the gradient. In Pure, we know that we can use differentiation to find the gradient function. So actually, velocity is equal to ds dt. Because ds dt means the rate of change of distance or displacement. So velocity is the rate of change of displacement. If you think about a displacement time graph, so there's time and this is the displacement, you know from GCSE that the gradient of that line was the velocity. So ds dt is differentiating displacement, which is s, with respect to time. That would give you the gradient, which is what the velocity is equal to. Another thing that I know about it being the rate of change is ds. S is a measurement that you would take in meters, and t is a measurement that you would take in seconds. So again, you've got velocity is meters divided by seconds, or meters per second. So you can see all of the units, everything kind of all coming together. We also know that acceleration is the rate of change of velocity. Okay, it's the rate of change of velocity that we have as well. So it's the rate of change of velocity, and again, it's also the second derivative of the displacement, because dv dt is ds dt. So if you differentiate ds dt again, you get d2s dt squared. So acceleration you find by differentiating the velocity with respect to time, and then you differentiate it again. Sorry, not the velocity again. You differentiate the displacement twice, or the velocity once, to give you the acceleration. And there's a bit of a way of memory about how we might think about to do these kinds of things here. So the way I picture this is it changes between S, V, and A, okay? And the way I remember it goes in that order, S, V, A, is because of Suvat. It goes S, U, V, A, T. So the three things you've got, displacement, velocity, and acceleration, they follow the same order as Suvat. And to go from S to V, you differentiate. And to go from V to A, you differentiate. And the way I also remember that is differentiation goes down in that little thing that we've got written here. And then integration is going like up or increasing. And we'll use this a little bit more in a second. So this one says a particle P is moving on the x-axis. And sorry, this will all hopefully make a bit more sense when we look at an example. A particle P is moving on the x-axis. At time t seconds, the displacement x meters from O is given by x equals this particular function, t to the power of 4 minus 32t plus 14. It wants us to find the velocity of P when t equals 3. Well, if I just substituted in t equals 3, what would it be showing me or telling me? Yeah? It would just be showing us the distance, because we've just been told what the displacement is. So if I just substituted t equals 3 in, I would only be finding the displacement. But they've clearly asked for the velocity. Now we know if x is equal to t to the power of 4 minus 32t plus 14, although we used s just now, we're using the letter x. That's the two most common letters that they will use for this. If I differentiate this, if I do dx and I differentiate it with respect to time, what would it be the same as? What is dx dt going to be the same as? It's just the same as the velocity. So you differentiate the displacement to get the velocity. And then if we were given the velocity, you can differentiate the velocity to get the acceleration, because we're always talking about these gradients. So when you differentiate the displacement, you'll get velocity. So you get 4t cubed minus 32. This is what the velocity is. The velocity is 4t cubed minus 32. But we've been told that t is equal to 3. So the velocity must be 4 times 3 cubed minus 32. Which is 76? 76, and the units will be meters per second. So just to remind us where we were here for this question, we started off with the displacement. We wanted velocity, so we did this bit. We differentiated to go downwards to find out what the velocity was. Now we know that this thing here is the velocity. We can answer some of the next bits of the question. It says, find the value of t when p is instantaneously at rest. If it's at rest, what does that mean? It means that v is equal to 0. So we've now got that v equals 0. So 0 equals 4t cubed minus 32. Add the 32 and divide by 4, and you get 8 is equal to t cubed. So t is equal to 2. I'm just going to pause there to put this on Desmos, on the graph. I'll just freeze that while you guys are looking at it. Okay, so this is the graph. The graph that I've drawn, ignore these should say t, okay? The graph that I have drawn here is the displacement graph. So to begin with, the particle is here and it's travelling backwards and it goes all the way to the bottom and it travels forwards again. And we just said at 2 seconds it is at rest. What property do we see of it being at rest? The turning point, okay? Remember, this is displacement, so the gradient of the displacement is the velocity, so it makes sense that the gradient down here is 0 because it's when it's not moving at all. Now, the last part of the question for part C says, find the acceleration of p when t equals 1.5. Okay, well, I don't have what the acceleration is, so to find the acceleration, which is down here, I need to differentiate the velocity. So the velocity is 4t cubed minus 32. So I'm going to find dv dt, which is the acceleration, which is just 12t squared. Just differentiating it again to find the gradient of the velocity. And we know that t is 1.5. So the acceleration is 12 times 1.5 squared, which is 27 meters per second squared. if I wanted to here, if I wanted to go straight to the acceleration, I could have found out the second derivative of the displacement. Because the first derivative will give me the velocity, the second derivative will give me the displacement. So you could have done this thing, which is the same as this thing. These three things here are all equivalent to each other. So that's it with some differentiation. I'm going to do, I think, one more on this next bit. I'll just give you a chance to just finish writing that bit down.
The example of just doing straight to d squared.
Say that again.
Do the example of just doing straight to d squared.
To do this one here, yeah. So if I had this thing that I was told like this, while I'm just on that bit, imagine they didn't ask me about the velocity. If x was t to the 4 minus 32t plus 14, and they said find out what the acceleration is, okay, we would differentiate it and get 4t cubed minus 32. And then we would differentiate it again, and you know that notation from with Mr. Udin, right? And you would get this here. So this one is the displacement that they told us. This one is the velocity, and this one is the acceleration. So I could have written that as dv dt, because this thing is actually v as well. So you go from that one, you differentiate to get acceleration. What we're eventually going to look at is they might give you acceleration, and they might want you to go back to displacement. Well, it's pretty obvious what you're going to do to go backwards. You're going to integrate, and you're going to do integration. Okay? So we're going to do this one more question about the cat before I get you to do some practice. A cat's displacement from a house in meters is t cubed minus 3 over 2t squared minus 36t, where t is in seconds. Determine the velocity of the cat when t equals 2. At what time will the cat be instantaneously at rest? And what is the cat's acceleration after 5 seconds? So we're going to actually go, sometimes it's, we're going to write these things out to begin with, but sometimes you might like to say, doing all the differentiation at the beginning, that might be something that you find helpful. So S is the displacement here. This time I'm going to differentiate it once to find out what the velocity is. And the velocity will then be 3t squared minus 3t minus 36. So that's what ds dt is. And they want us to find the velocity when t is equal to 2. So when t is equal to 2, v is equal to 3 times 2 squared minus 3 times 2 minus 36. Which is just minus 30 meters per second. Sorry. Part B says, what time will it be instantaneously at rest? So Nabil, if it's saying it's instantaneously at rest, what am I going? What information is that giving me?
It could be like stopping at a certain point.
Good. And how would I then? How would I actually go about solving this? What value is that telling me about? If it's telling me it's at rest, what's it telling me about t or v?
T will be 0.
T is 0.
Yeah, T.
No, v will be at 0. The rest means that v is at 0. So we're going to then say this thing is equal to 0, which you can either put on your quadratic solver or you can divide by 3, presumably factorize this. Yeah, so t is how much? 4 and minus 3.
Yeah.
Okay, good. I'm just trusting you here. What if you divide by 3? Oh, yeah, of course. T equals 4. T equals minus 3. Does it make sense to have the t as minus 3? Nope. So we're just going to stick with the t equals 4 because we want it to be a positive time that we've got there. And then part C of the question, what is the cat's acceleration after 5 seconds? So I'm going to differentiate to get the acceleration. So I can either I can find the second derivative of this, or I can do dv dt. I can either do dv dt, which is the same as the second derivative of the first one, whichever of those notation you prefer, either of those is fine. And I'm just going to differentiate this again to get 6t minus 3. So my acceleration is 6t minus 3, and we've been told that t is 5. So it's 6 times 5 minus 3, which is 27 meters per second squared, which is pretty fast for a cat. All of this is like insanely fast for a cat. Okay, this is probably not a very real life situation here. If you're still writing that down, that's absolutely fine. If you've finished writing it down, just have a think about what happens to the type of expression that we have for the displacement, then the velocity, and then the acceleration. What do you see happening from the displacement to the velocity to the acceleration? How would you describe the change in those functions? Say that louder.
Cubic to a quadratic, then a linear.
Good. It's gone cubic, quadratic, linear. If it was a power of 4, it will go to a power of 3 and then a power of 2. Okay, so you're always going to see these kinds of patterns that you've got here. Okay, so we're going to do some questions from 11b here. I'll pick out the ones you want to do.